Good morning to all. Jai Hind. Today I am here to deliver my first lecture based on the fluid mechanics. So let us start. First slide show the table of contents in which I will cover the various topics, basic concepts and definitions, distinction between a fluid and solid, properties of fluids, viscosity, kinematic and dynamic viscosity, variation of viscosity with temperature, Newton law of viscosity, type of fluid, surface tension and capillarity action, and last slide will be referencing. So, what is the definition of a fluid? So, fluid is a substance that can be flow and take the shape of its container. So, what is a fluid? Fluid is a substance that can flow and take the shape of its container. Fluid contains liquids and gases. Now, basic concepts and definitions. So, first of all, we will define fluid mechanics. So, fluid mechanics is that branch of engineering science which deals with the behavior of the fluids at rest as well as in motion. Means fluid mechanics is basically a branch of engineering in which we will consider the fluid at rest as well as in motion. So if the branch of science deals with the its different types of motion, then their classification will be in the same way. For example, the branch of science deals with the static, kinematic and dynamic aspects of fluids. So if the fluids study includes its rest position, then this types of study of fluids is known as the fluid statics. The study of fluids in motion where pressure forces are not considered is called fluid kinematics, and if the pressure forces are also considered for the fluid in motion, that branch of science is called as fluid dynamics. Means basically there are three types of fluid study. For example, fluid static, kinematics and dynamic aspects. In case of fluid statics, the fluids are considered at rest, whereas in case of fluid kinematics, fluids are considered in motion but pressure forces are not considered, while in case of fluid dynamics, fluids are also considered in motion with the consideration of the pressure forces. Okay. Now, what are the distinction between fluids and solids? So, fluids means liquid and gas, and solid and solids. So, solids have the basic characteristic that is it has a definite shape and volume. Solid has a definite shape and volume, and it can maintain their shape unless a force is applied. Whereas in case of fluids do not have a definite shape. Means it have not a definite shape. It can change its shape depending on the container. The fluids take the shape of their container. So these are the basic differences between the solids and fluids. Now, various properties of fluids we have to study here. So the first property of a fluid is the density or mass density. So how one can define the density or mass density? So the density of fluid is defined as the ratio of mass of the fluid to its volume. The density of fluid is represented by the rho. Rho means density of fluid equal to mass divided by volume. If we consider its units, so mass is measured in kilogram, whereas volume is measured in meter cube. So the final unit of density will be kilogram per meter cube. If we consider the standard value of density for water, then it is taken as 1 gram per meter cube or 1000 kilogram per meter cube. Next, specific weight or weight density. So what is the specific weight or weight density? It is basically a parameter. By using this parameter, we can compare the relative heaviness of one fluid with respect to another. So let us see how it is defined. The ratio between the weight of fluid to its volume means specific weight is represented by omega. In some books it is also represented by gamma, like this. But here it is represented by omega, where omega is defined by weight of fluid divided by volume of fluid. So weight means mass into acceleration due to gravity divided by volume, capital V. So if we consider m by v, so m by v can be replaced by density or mass density. Therefore omega can be written in terms of mass density into acceleration due to gravity. Its unit will be Newton per meter cube. If we consider the standard value for a particular type of fluid, for example here the value of specific weight for water is considered as 9.81 into 1000 Newton per meter cube in SI units. So this value is standard for water, means specific weight of water is considered as 9.81 into 1000 Newton per meter cube in SI units for all its application. Next, specific volume. So what is the specific volume? If we see this formula, then specific volume is defined as the volume of fluid divided by mass of fluid. So basically it is a reciprocal of the mass density. Okay, or in terms of mass density we can also write it 1 divided mass of fluid divided volume of fluid, or simply this term can be replaced by the density, that is rho. So it will be equal to 1 by rho. So specific volume is equal to the 1 by mass density. So specific volume is the reciprocal of the mass density. It is expressed as meter cube per kilogram. It is basically applied to the gases, means specific volume is basically applied for the gases. What is the specific gravity? Specific gravity is defined as the ratio of the weight density of a fluid to the weight density of a standard fluid. So specific gravity is defined as the ratio of the weight density of a liquid to the specific weight or weight density of a water. For example, in case of liquid, it will be considered as a liquid, and a standard material for the comparison will be taken water. In case of gases, the standard will be taken as the air. So if we define the specific gravity for liquids, so specific gravity for liquid can be defined as the weight density of liquid divided by weight density of water, whereas in case of specific gravity for gases will be equal to the weight density of gas divided by weight density of air. Now weight density of liquid can be also written as equal to S into weight density of water equal to S into 1000 into 9.81 Newton per meter square, per meter cube, sorry. So density of liquid can be written simply in terms of density of water as S into density of water. Okay, and density of water will be 1000 kilogram per meter cube. So density of a liquid can be simply written in terms of density of water as density of liquid equal to the sorry, S into 1000 kilogram per meter cube. Now let us some basic example based on the previous definitions. For example, in this example, calculate the specific weight, density and specific gravity of 1 liter of a liquid which weighs 7 Newton. Means in this case, this problem we have to calculate the specific weight, density and specific gravity of 1 liter of liquid. Means in this problem volume of liquid is given, volume 1 liter, and its weight capital W is given by 7 Newton. So let us see the given data, that is volume is 1 liter and weight is 7 Newton. So we have to calculate the specific weight, density and specific gravity. If we convert the volume of a fluid in a meter cube, then it will be 1 liter equal to 1 by 1 divided by 1000 meter cube. It is a standard conversion formula. One should always learn. Okay. So let us calculate the first parameter, that is specific weight. So specific weight is defined as the weight divided by volume. Okay. Weight is already given in the problem, 7 liter, and its volume is 1 divided by 1000 meter cube. If we put these two values, then specific weight will be equal to 7000 Newton per meter cube. Okay. Let us calculate the second parameter, that density. Density is already defined, that is the mass of one volume, but in terms of specific weight, we can also write it as specific weight divided by g, means acceleration due to gravity. Therefore, specific weight is already calculated. Put these two values and its final value, that is the final value of density will be 730.5 kilogram per meter cube. Okay. Now the specific gravity. So specific gravity is earlier defined by density of liquid divided by density of water. Okay. So density of liquid is already calculated, that is 713.5 kilogram per meter cube, and density of water is the standard value, that is the 1000 kilogram per meter cube. So put these two values and final value will be 0.7135, and it is unitless, it has no dimension, therefore it will give only a magnitude. So specific gravity, final value of specific gravity is 0.7135. So if we learn the basic definition of the parameters, then you will easily calculate these parameters. Okay. So let us discuss the next example. We have to calculate the density, specific weight, and weight of 1 liter of petrol of specific gravity 0.7. In the previous problem, we have to calculate the specific gravity, but in this question, specific gravity is given. Okay, and further we have to calculate the density, specific weight, and weight of 1 liter. So in this problem, volume is already given, that is 1 liter. Okay, it can be converted into meter cube. So specific gravity, that is S equal to 0.7 is given. So let us calculate the first parameter, that is density. So density is calculated by using the specific gravity formula also. So earlier we have discussed in terms of density. Density can be defined in terms of specific gravity as S into 1000. 1000 is the standard density of water. So if you put the specific gravity, so density of the given liquid or fluid can be calculated. So put the value of S, that is S equal to 0.7. Final value of density will be 0.7 into 1000, that is 700 kilogram per meter cube. Okay. Next, specific weight. Specific weight means W equal to rho into G. So specific weight will be rho into G, and rho is already calculated 700, and G is the G has its standard value 9.81. So final value of the specific weight will be 6867 Newton per meter cube. Okay. Now the last parameter, that is the weight of fluid, that is petrol, should be calculated. So if we look at this formula, that is the specific weight is equal to weight upon volume. Okay, or in terms of symbol W, that is specific weight, equal to capital W divided by volume, and volume is 1 liter, and if you convert in meter cube, it will be 0.001 meter cube. Okay, and capital W, we have to calculate the capital W, and this is the specific weight. which is already calculated here. Specific weight 6867. So put value of the specific weight and final value of capital W means weight of petrol can be calculated as 6867 into 0.001. It will be equal to 6.867 Newton. Okay. So these two examples are based on the basic parameters, that is the mass density, specific gravity, and other parameters. Okay. Let us move towards the next topic, that is the viscosity. So what is the viscosity? Let us discuss. It is defined as the property of fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. Means viscosity is the property of fluid which offers the resistance between the relative motion of adjacent fluid layers. Okay. For example, if we consider this diagram showing the velocity variation near a solid boundary, on x-axis velocity parameter is mentioned and at y-axis depth of fluid layer is mentioned. So suppose this is the first layer of the fluid, okay, and this is the second layer of the fluid. The motion of fluid is in positive x direction. So if we consider the viscosity, then these two fluid layers will apply an internal resistance to each other. Okay. So this property of fluid is known as the viscosity of the fluid. Okay. Now when two layers of fluid, suppose at a distance dy, apart, move one over the other at different velocity, say u and u plus du, as shown in this figure, the viscosity together with the relative velocity causes a shear stress acting between fluid layers. So when an internal forces or resistance will be developed during the relative movement of two fluid layers adjacent to each, then it will create the shear stress. Okay. Now the value of shear stress is proportional to the rate of change of velocity with respect to y. Means the value of shear stress developed between these two layers is proportional to the rate of change of velocity with respect to the depth, that is the y. Okay. And this can be represented as tau. Okay. Tau is basically shear stress. Okay. So mathematically tau is proportional to the du by dy. Du is rate change in velocity and dy is change in depth. So du by dy is representing the change in velocity with respect to depth, or we can write it as sorry, tau is equal to mu du by dy. Okay, where du by dy represents the rate of shear strain or rate of shear deformation or velocity gradient. Okay, du by dy is known by these three parameters. Okay, and mu is known as the constant of proportionality, and it is also known as the coefficient of dynamic viscosity or only viscosity. Okay, so mu is the coefficient of dynamic viscosity, or in simplified form we can only call it as viscosity. Okay, so from this equation 1.2, mu can be written as tau divided by du by dy. Okay, so what will be the unit of viscosity? If you put the unit of these two parameters, then final unit of the coefficient of viscosity can be calculated. For example, tau is the shear stress. Okay, and du by dy means change in velocity, change of velocity, and dy means change of distance. Okay, so shear stress is equal to basically force divided by area, or change of velocity means length divided by time into change of distance with 1 by length. If we finally simplify it, then final value of mu will be force into time divided by length square. So everyone knows the basic unit of these parameters. So final unit of mu will be Newton second divided by meter square, or we can represent it as Newton second per meter square. Okay, so this is the unit of coefficient of viscosity or dynamic viscosity. Similarly, another term, that is the kinematic viscosity, can be defined as the ratio of dynamic viscosity divided by density of that fluid. Okay, so what will be the unit of kinematic viscosity? Its unit will be, put the value of mu, that is the coefficient of viscosity, Newton second divided by meter square, and density means mass upon volume. So if we put the value of these two parameters, the final value of kinematic viscosity will be meter square per second. Okay, in CGS system, what will be the unit of kinematic viscosity? In CGS system, length can be measured in centimeter square and time is measured in second. So in CGS system, the unit of kinematic viscosity will be centimeter square per second, and it is also known as stoke. So 1 stoke will be equal to 1 centimeter square divided by second per second. Okay. Now let us move towards the next important topic, Newton's law of viscosity. So what is the Newton's law of viscosity? It states that the shear stress, that is the tau, on a fluid element layer is directly proportional to the rate of shear strength. Means tau is directly proportional to the rate of shear strength, or du by dy. Okay, the constant of proportionality is called the coefficient of viscosity, which is earlier we have discussed. Okay, so mathematically it can be represented by the equation number 1.2, that is 1.2 tau is equal to mu du by dy. Means equation 1.2 is also known as the Newton's law of viscosity, in which shear stress is equal to the mu du by dy. Okay, fluids which obey the relation are known as Newtonian fluids. So all the fluids which follow the rule, that is tau is equal to mu du by dy, is known as the Newtonian fluid. Okay, and all the fluids which don't follow the Newton's law of viscosity are known as the non-Newtonian fluids. Okay, so basically according to Newton's law of viscosity, there are two types of fluids. First one is the Newtonian fluids, which obeys the Newton's law of viscosity, and which don't follow the Newton's law of viscosity are known as the non-Newtonian fluids. Now let us discuss the variation of viscosity with temperature. So what will be the effect of temperature on the viscosity? Okay, so let us first discuss the effect of temperature on the liquid. Okay, the viscosity of liquids decreases with the increase of temperature, while the viscosity of gases increases with the increase of temperature. Okay, so if we consider the effect of temperature on the viscosity, then research has revealed that if we increase the temperature of a liquid, its viscosity will if we increase the temperature, then viscosity of liquid will be decreases, and in case of gases, if we increase the temperature of gas, then its viscosity will also increase. Okay, this is due to the viscous forces in a fluid, or due to cohesive forces and molecular momentum transfer. Means there are two parameters which governs the viscosity of a fluid. For example, if we consider the first case, that is the liquid, in case of liquid, the viscosity is governed by the cohesive forces primarily, and molecular momentum transfer forces by secondarily. Okay, secondary. So if we increase the temperature of a liquid, its cohesive forces will be decreased. That's why in case of liquid, if we increase the temperature, its viscosity will be decreasing. Whereas in case of gases, the molecular moment of transfer forces are primarily predominant. That's why if we increase the temperature, then molecular moment of transfer forces will be activated and it will increase the motion of gas particles. That's why its particles will come closer to each other and therefore finally the viscosity will be increasing. Okay, so this is these are the description of variation of viscosity with temperature. Now there are two formulae given here. One is for liquid, which shows the variation of viscosity coefficient with respect to temperature. For example, U is equal to U naught or mu naught into 1 by 1 plus alpha t plus beta t square. From this equation we can easily conclude that mu is inversely proportional to the T. Means if we increase the value of temperature, then coefficient of viscosity will decrease. Okay, where mu is the viscosity of liquid at T degree Celsius, implies mu naught is the viscosity of liquid at 0 degree Celsius, implies alpha and beta are constant for the given type of liquid. Okay, if we consider for water, then mu naught is 1.79 into 10 raised to the power minus 3 pi. Alpha and beta have the constant value as mentioned here. Okay. Now for gases, mu is represented as mu naught plus alpha t minus beta t square. Okay, where mu naught and alpha beta are the given constant for given type of gases. So we can easily calculate the value of coefficient of viscosity using these constant parameters and putting the value of temperature for certain type of gases. Okay. Further, one can conclude that if we increase the value of temperature, then coefficient of viscosity is also increases. Now, types of fluid. Okay. So there are the 5 types of fluids are classified. First one is the ideal fluid. So what is the ideal fluid? Before discussing about the ideal fluid, one should know that in reality or in practical life there is no one thing is existed in ideal conditions. Okay, so let us discuss the ideal fluid. What is the ideal fluid? Ideal fluid is incompressible and is having no viscosity, is known as an ideal fluid. Means ideal fluid will be incompressible and having no viscosity. Okay. Further, ideal fluid is only an imaginary fluid, as all the real fluids which exist have some viscosity. Means ideal fluid is basically hypothesis, or it is an imaginary concept, but in reality there is certain value of compressibility and viscosity. Okay, if we see the diagram here, which is represented the shear stress and velocity gradient. So ideal fluid is basically represented along the x-axis. Okay. Now the second, that is the real fluid. A real fluid which causes viscosity is known as real fluid. All the fluids in actual practice are real fluids. Okay. For example, whatever types of fluid motion is considered in for practical applications, okay, these all fluids are considered as a real fluid. Okay. Now, Newtonian fluid, a real fluid in which the shear stress is directly proportional to the rate of shear strain, is known as a Newtonian fluid. Okay. So let us discuss in the diagram. This is straight line representing the variation of shear stress and velocity. Okay, and this is represented as straight line. Means a Newtonian fluid represents the linear behavior of shear stress with respect to the strain or shear deformation. Okay. Now non-Newtonian fluid, a real fluid with which shear stress is not proportional to the rate of shear strain or velocity gradient, known as a non-Newtonian fluid. So let us see where is the non-Newtonian fluid. This curve is known as the non-Newtonian fluid. So one can easily conclude about these two curves, differences between these two curves. Newtonian fluid basically follow a linear pattern. Means if we increase the velocity gradient, then shear stress will be also increased in the same proportion. Whereas in case of non-Newtonian fluid flow, if we increase the velocity gradient or changes in the velocity gradient, does not necessarily need to maintain the same proportion of the shear stress. Okay. For example, this curve is showing linear behavior up to this point. Okay, and after this point, its behavior is changes. Okay. Now last one is the ideal fluid, ideal plastic fluid. What is the ideal plastic fluid? A fluid in which shear stress is more than the yield value and shear stress is proportional to the rate of shear strain is known as ideal plastic fluid. So in ideal plastic fluid, shear stress is more than the yield value. Means if we see in this figure, ideal plastic fluid starts from here. Okay, means in case of velocity gradient value is 0, then ideal plastic fluid have some value. This value is the yield point. Okay. Now and after this point, ideal plastic fluid is varies as per this behavior, linear behavior. Okay. Now let us discuss the example based on the previous concept. That is, if the velocity distribution over a plate is given by u equal to 2 by 3 y minus y square, in which u is velocity in meter per second at a distance y meter above the plate, determine the shear stress at y equal to 0 and y equal to 0.15 meter. Take the dynamic viscosity of fluid as 8.63 poisons. Okay. So in this question, a general equation for governing the motion is given. U equal to 2 by 3 y minus y square, and in which velocity at different point, means have to not velocity, shear stress at different point have to be calculated. Okay. For example, shear stress at y equal to 0 and y equal to 0.15 meter have to be calculated, where dynamic viscosity means coefficient of dynamic viscosity mu is already given 8.63 Poisson. So let us solve this problem. U equal to 2 by 3 y minus y square. So how one can get the value of du by dy? If you differentiate these terms with respect to y, it will be du by dy. So if you differentiate one time with respect to y, then it will become 2 by 3 minus 2y. If we put the value of y at equal to 0, then it will give the rate of velocity variation with respect to y equal to 0. So put the value of y equal to 0, it will give the velocity variation at y equal to 0. Similarly, if we put value of y equal to 0.15, then it will give the velocity variation with this, at y equal to 0.15, it will be equal to 0.367. Now value of mu is 8.63 points. If we convert it in SI units, it will be divided by 10. So the value will be finally 0.863 Newton second per meter square. Now use the basic formula, that is Newton's law of fluid flow. Mu tau is equal to mu into du by dy. Okay. Now we have already the value of du by dy at different positions, and mu is already calculated from this value. Okay. Put these values, that is mu into du by dy, y equal to 0. It will give the shear stress at y equal to 0. It will equal to 0.5756 Newton per meter square. If we put the value of y equal to 0.15, then it will give the shear stress at distance y equal to 0.15 meter, which is the requirement. So the final value equal to the 0.3167. Sorry.